On August 4, 2020, at approximately 6:08 p.m. local time, a massive explosion occurred at the port of Beirut, Lebanon, making it one of the most powerful non-nuclear explosions in history. The blast resulted in at least 218 fatalities, over 7,000 injuries, and displaced approximately 300,000 individuals. The 2020 explosion at the port of Beirut was one of the most powerful non-nuclear explosions in history. It was triggered by the ignition of approximately 2,750 tons of ammonium nitrate that had been stored unsafely in Warehouse 12 at the port since 2014. The ammonium nitrate was confiscated from the cargo ship MV Rosas and stored without adequate safety measures. The failure to remove the materials from the warehouse and relocate them was attributed to mismanagement of the port, corruption of the government, and inaction of the flag registry's country and ship owner. Major accidents involving ammonium nitrate and its fertilizers, while not uncommon, are preventable, and their impacts can be mitigated through the effective use of available security and safety standards. All regions face risks. In the Pan-European region and North America, examples of accidents include the Toulouse fertilizer plant explosion in France 20 years ago and the 2013 West fertilizer plant explosion in the United States. In other regions, examples from the last decade include the 2015 Tianjin port explosion in China, and the 2021 Bata explosions in Equatorial Guinea, among others. Investigations by Forensic Architecture, in collaboration with fire safety experts, analyzed witness footage and conducted fire dynamic simulations. The presence of flammable materials such as fireworks and car tires stored alongside the ammonium nitrate contributed to the fire's escalation. Their analysis suggests a sequential origin of the events. Over a period of 14 minutes, a series of fires and explosions developed, generating distinct plumes from various sections of Warehouse 12, each with unique shapes and colors reflecting the different materials burning. The incident began at 5:54 p.m. with the first plume shifting from white to a darker shade. By 6 p.m., a thick, black plume emerged, indicative of burning car tires. A larger plume, signaling the ignition of fireworks, then manifested at 6:07 p.m. The culmination occurred at 6:08 p.m., when a symmetrical, spherical plume erupted from the building center. This marked the single point of the massive ammonium nitrate explosion. Within 9 seconds, a reddish-brown plume shot 755 meters skyward, ejecting tons of particles. This distinctive color is attributed to the presence of nitrogen oxides, a byproduct of the ammonium nitrate's violent decomposition. The catastrophic detonation of ammonium nitrate resulted from a severe breach of international safety standards for its storage in Warehouse 12. These standards dictate strict rules for quantities, container arrangement, stacking, and critical distances to residential buildings. For the observed quantity, a minimum safe distance of 1,570 meters was required to minimize risk, yet damages extended beyond this safety radius. Despite ammonium nitrate's inherent resistance to fire alone, the 2,750 tons were stored in bulk, in close proximity to highly incompatible and flammable materials, including fireworks, ammonium phosphate, and car tires, without adequate ventilation or fire suppression. This hazardous combination of confined, high quantities and contamination effectively created a made bomb scenario, leading to the catastrophic explosion. The Beirut port explosion's yield was widely estimated between 0.5 and 1.12 kilotons of TNT, making it one of the largest accidental non-nuclear explosions ever recorded. This estimate was derived from various analyses, including social media video footage, seismic data, ranging from a 3.3 to 4.5 magnitude earthquake equivalent, and infrasonic data. The energetic event exhibited a magnitude detectable from Cyprus, an approximate radial distance of 200 kilometers from the hypocenter. The extensive energy dissipation created a crater with a depth of 40 meters at the incident site. Furthermore, the blast wave propagated to an extent that resulted in the structural collapse of approximately 70,000 residential and commercial edifices, and the incapacitation of 6 maritime vessels via submersion. Ammonium nitrate is a compound used in both fertilizers and explosives. Is stable under normal conditions but can undergo a rapid, violent explosion given specific triggers. Its inherent danger stems from containing both an oxidizer, nitrate anion, and a fuel, ammonium cation, within the same molecule, providing an internal oxygen source that fuels rapid combustion. Explosive decomposition is highly sensitive to contamination. Organic materials, like fuel oil, tires, or even coffee, or certain inorganic impurities act as fuels, significantly lowering the energy required for detonation. Confinement. Heating ammonium nitrate in a confined space builds pressure from released gases, accelerating the reaction into a runaway explosion. Strong shock. An external explosive force can directly initiate detonation. The explosion itself is a highly exothermic process, releasing substantial heat that accelerates the reaction into a feedback loop. This leads to the near-instantaneous conversion of solid ammonium nitrate into a massive volume of hot gases, generating a powerful shockwave capable of widespread destruction. Temperatures can reach 1,800 degrees Celsius to 2,000 degrees Celsius. While low-temperature decomposition of ammonium nitrate yields nitrous oxide and water, explosive detonation at high temperatures, especially with confinement or contamination, becomes far more energetic, producing molecular nitrogen and oxygen, and water. The presence of organic contaminants leads to a more complex reaction, akin to an ammonium nitrate fuel oil explosion, forming gases like carbon dioxide in addition to nitrogen and water. Crucially, large ammonium nitrate explosions often release toxic, reddish-brown fumes, which are primarily nitrogen dioxide gas. This indicates incomplete decomposition and the formation of various nitrogen oxides under the extreme conditions of the explosion. The 2020 Beirut port explosion, caused by ammonium nitrate, had significant and multifaceted environmental impacts. Air pollution. The explosion released substantial amounts of toxic gases, primarily nitrogen oxides, including nitrogen dioxide, which caused the visible reddish-brown plume. Ammonia and carbon monoxide were also released. While initial high concentrations of nitrogen dioxide dissipated within about a week, the blast also generated massive quantities of particulate matter and dust from pulverized buildings and materials. This dust, potentially laced with hazardous substances like asbestos, lead, and other heavy metals, posed a long-term risk, especially during ongoing demolition and reconstruction, which significantly elevated ground-level particulate matter 2.5 concentrations. Water contamination. The blast created a large crater that filled with seawater, and there were concerns about chemicals seeping into the marine environment. The release of nitrogen oxides and ammonia into the atmosphere could also lead to acid rain, impacting aquatic ecosystems. The explosion also damaged port infrastructure, increasing the risk of further chemical leakage into the sea. The immense volume of construction and demolition waste, estimated between 100,000 and 800,000 tons, likely contained hazardous chemicals, including pesticides, pharmaceuticals, industrial chemicals, lead from old pipes, and heavy metals. This waste posed a significant threat of contaminating soil and groundwater through direct exposure or leaching. Ecological damage. the release of noxious gases and potential water contamination posed a threat to ecosystems, with amphibians and aquatic life being particularly vulnerable to nitrate poisoning as decomposition products transferred to the ocean. The destruction of the port and surrounding areas also disrupted local habitats. The Beirut explosion underscores the critical importance of proper hazardous material storage and regulatory oversight. Key recommendations include strict compliance with storage regulations. Hazardous materials like ammonium nitrate must be stored following international safety standards, ensuring separation from flammable substances and proper ventilation. Regular safety inspections. Facilities storing hazardous materials should undergo frequent inspections to ensure compliance with safety protocols. Emergency preparedness. Ports and storage facilities must have robust emergency response plans, including fire suppression systems and evacuation procedures. Transparent governance. Authorities must maintain transparent records of hazardous material storage and ensure accountability in regulatory enforcement. Preventing major accidents involving ammonium nitrate and ammonium nitrate-based fertilizers hinges on effective risk assessments, land use planning, and proper siting. These assessments help authorities and industries understand potential damage and necessary safety measures. This critical information should guide national and local authorities in land use planning and siting decisions for these hazardous activities, considering factors like proximity to populated areas, transboundary impacts, and environmental effects. The United Nations and the OECD have emphasized the need for improved management of hazardous substances in port areas to prevent similar disasters. The Beirut port explosion stands as a profound and tragic reminder of the immense power within seemingly ordinary substances, and the dire consequences when critical safety protocols are neglected. Understanding the chemistry, the conditions, and the devastating impact of events like this isn't just about recounting history. It's about learning vital lessons to safeguard our future. What takeaways resonate most with you from this complex disaster? Share your insights and questions in the comments below. We love hearing from you and fostering a deeper understanding together. If this deep dive helped illuminate the science behind this powerful event, please give this video a like and consider subscribing to the channel for more explorations into the fascinating, and sometimes perilous, world around us.